Thanks so much, Michael, and thank you so much for the support again. So the first talk will be analysis and optimization of resilience in blockchain peer-to-peer networks. The second one will be about the transaction network, specifically to XRP. Okay, so I think most of us know that most blockchain systems run on a peer-to-peer overlay communication network. There is no centralized server. Communication going through, let's say, messages about the blocks will take place over nodes that have a link in this peer-to-peer network. And as a consequence, the resilience and overall reliability of the blockchain system really depends on the topology of this peer-to-peer overlay. The main goal of this project was to analyze and potentially optimize the topology with respect to adversarial attacks and random failures. And a typical adversarial attack could just be a denial of service attack. And a specific case of interest was the peer-to-peer network of Ripple or XRP. The data set that we used, important piece of information here is that XRP Ledger has a native crawler, so anybody can actually get this data at any point in time. The specific data set we relied on was from this paper by Thomas et al. From 2023, where they crawled the data from, again, XRP's peer-to-peer overlay from the period of January to May 2022. But we are in the process of getting more data on this one. A number of features of this topology are listed here. The things that we should remember for the rest of the talk are, this is not a huge network. The number of nodes is about 1,000, a little less than that. And it's a bidirectional network. In degree and out degree will be the same, the number of connections a node has. And it turns out to be average about 16 connections per node. And at all times during this period, this network happened to be a connected one, meaning that between any pair of nodes, there was a path of links that they could communicate over. So with that in mind, let's look at what this network becomes if some of the nodes are removed. So that's part of the resilience analysis. The attack model, so to speak, here is that the adversary maybe launches an attack and manages to remove some of the nodes from the network. We consider both random attacks, where the adversary just uniformly at random selects the nodes to remove from the network. With this mindset, it could easily also model random failure of the nodes. The second part of it is going to be targeted attacks, and we will consider like different types of attack strategies. So when you consider a communication network, what type of resilience metrics we would use? Typically, we look at the remaining network and see what are its maybe connectivity features. When I remove, let's say, 10% of the nodes or 20% of the nodes, is the rest of the network still relatively well connected, or is it maybe something that disentangled into really small pieces that are isolated, disjoint from each other, so we cannot really think of this really supporting the blockchain system anymore because it's basically just single, perhaps isolated nodes. So with that mindset, the typical metric, let me see if I have my mouse here, is let's say the size of the largest connected component of the network in the remaining part. So I fail, let's say, p fraction of the nodes. I look at the rest of the network and see its largest connected component and its size. Typically, you will get maybe a curve like this. Another set of metrics you could be interested in are this critical point P star, at which point everything seems to collapse. You may also want to compute the area under this curve, maybe to get a general understanding of how robust or resilient this network is with respect to different sizes of attacks. Let's look at some results. For random failures, it seems like this network is extremely robust. We are pretty much looking at a linear decline here, which means that no matter how many nodes you really fail, the rest of the network seems to be still staying connected, which is a great feature. But when it turns out to, when we turn out to targeted attacks, in particular, we considered here an attack that targets the highest degree nodes that are the most connected ones. The robustness seems to be not as good. You see a relatively sharp decline here at about like 100 nodes removed from the system. The remaining 900 are no longer connected. The largest connected component among them is about 200 nodes. I'll show this figure again when we talk about the three strategies, three different attack modes. We will get back to it in a second. But the third type of attack we looked at is the so-called high betweenness attack. So betweenness centrality is a metric that is typically used in network science. It measures, how frequently a node is part of the shortest paths between other pairs of nodes. You can think of a high betweenness node as sort of a bridge. It connects a whole bunch of nodes on one side to a whole bunch of nodes on the other side that would otherwise perhaps not be connected. It is sort of in the passageway of a lot of shortest paths. So when the adversary actually targets high betweenness nodes, it seems like they can disentangle the network much faster than the high degree attack. So this is better seen in this particular figure where we see three types of attacks. The random, again, is pretty robust. High degree seems to be efficient early on, but there is a period where the attack is not as efficient anymore. The high betweenness seems to be the most effective if you want to really demolish this network and basically create this really isolated bunch of components. And when I look at this figure, I immediately thought maybe that could be another attack strategy that combines highest degree and highest betweenness, and maybe a metric could be obtained as a combination, and it could be even more efficient. So this is what the situation is, at least was back in 2022. But as an engineer, most of our work also has an eye towards improving things. So a part of the work was, can we impose some additional edges in this network and improve its resilience? And the idea here came from this model called random chaos graph that we worked on for a long time. It's really a simple construction. It's a random way of constructing the network where everybody picks k nodes uniformly at random, and the orientation of these edges are then ignored. You get a bidirectional graph or an undirected graph. And what we proved in the past was that even with k equals 2, which leads to a graph with average degree 4, this graph is almost surely connected. Even with a small number of nodes, we get almost surely a connected graph. So the idea was that, can we look at this construction and gain ideas to add edges to this network and potentially improve its robustness? And if you remember, the original network had an average degree about 16, and we are adding just 4 edges per node. And the figures here show that the robustness can be significantly improved. When it comes to random attacks, there was no room for improvement to begin with. The network itself was very robust. But when high degree nodes are attacked or high betweenness nodes are attacked, we see that the network is much more resilient. The curve is not as strong as perhaps the random attack, but you can see a significant improvement in the largest connected component size in the remaining network, which we feel like is a potentially good maybe strategy if we could control the topology. I think I'm running out of time, and this is my last slide for this talk. So the conclusion is, overall, XRP's peer-to-peer network seems to be pretty robust with respect to random failures, not as much for targeted attacks. Adding links through this random chaos construction seems to be like a good idea. And the future work could potentially consider whether we can, from the beginning, design this network using ideas, again, from the random chaos construction to make it really robust at the get-go. And can we also maybe look at a more optimization type of flavor? I just gave an idea where things are better, but I didn't really optimize anything. So could we make this more concrete? And of course, resilience of XRP's transaction network could be a future work, and it's going to be a future work that I will talk about in a second. Yeah. Which, should I just continue with that? Okay. Let's get it going. Okay, so yeah, thanks for the support for this one, and okay. So I need, okay.